Welcome back to the deep dive. Today we are looking at a stack of research that honestly feels a bit like a heist movie, but played out at the molecular level.
It really does. I mean, we're tackling a classic problem in pharma today.
Right, the undruggable proteome. We have these source papers laying out a framework to crack proteins that cause diseases, but seem to have absolutely no place for a drug to attach.
Yeah, they appear totally featureless, just like glass walls where a molecule simply can't grab on.
But the twist in this research is that undruggable is really just a failure of how we observe them, because these proteins aren't static statues, right?
Exactly. They vibrate, they breathe, and if you catch them at the right moment in that cycle, these cryptic pockets open up.
Just transient landing spots that appear and vanish.
Right, and the issue is standard models, even the big ones like AlphaFold, tend to miss them. They predict the most stable average structure.
They give you the statue, not the breathing organism. So the mission of the research we're looking at isn't just to build one better model. It proposes a hierarchical neurosymbolic multi-agent system.
Or HNS-MAS, which is quite a mouthful. But think of it as a specialized squad. Instead of one giant brain trying to do everything, you have 4 distinct agents hunting down these pockets.
Let's break down that squad for you. It starts with layer 1, the perceiver agent. The papers call this the tailor.
Which is a great analogy. The biggest hurdle with rare pockets is the out-of-distribution problem. General models get completely confused by unique, messy folds.
Because they're guessing based on what they've seen before, not what's actually right in front of them.
Precisely. So the perceiver agent uses protein test time training, or protein TTT. It literally retrains its internal parameters on the fly for that specific target protein.
It minimizes its own surprise, so to speak, customizing the suit before trying to wear it.
Right. Then it hands the prep data to layer 2, the planner agent.
The strategist of the group. This one uses a hierarchical reasoning model, which mimics human cognition.
Yeah, it has 2 modes. A high-level module for abstract strategy, which is slow thinking, and a low-level module for fast granular calculation.
Kind of like System 1 and System 2 thinking applied to protein folding. And it uses CLIO, right, cognitive loop, via in situ optimization.
Exactly. It monitors its own thought process. If the fast module gets stuck, the high-level one intervenes.
So it actually has metacognition. It knows when it's confused. But once you have the strategy, you still need to physically model the interaction, which brings us to layer 3.
The execution agent, or the engine, this runs on ISO-DDE, the Isomorphic Labs drug design engine.
And the benchmarks here are wild. On the hardest targets, it doubles the success rate compared to AlphaFold 3.
Because it models induced fit. It predicts exactly how the protein shape shifts to accommodate a new drug. It's engineering the pocket, not just finding it.
But how do we know it's not just hallucinating? We've seen AI do that before.
That is layer 4, the auditor agent, the safety net. It uses GraphMERT to cross-reference predictions with a massive knowledge graph of hard facts.
So it checks the deep learning probability against rigid biological logic, ensuring the pocket is actually biologically valid.
Right, it prevents the system from chasing a chemical impossibility.
What's fascinating to me is how they communicate. They treat protein geometry as a language using GOBE.
Yeah, GOBE tokenizes 3D structures into text. The AI reads the geometry like a sentence.
Which enables this crazy alive system called the Darwin-Gödel machine.
That's the step toward full autonomy. The system rewrites its own code based on what works. It evolves without human help.
And finally, O-Design steps in to generate the specific molecule that fits the newly found pocket.
Moving drug discovery from finding a needle in a haystack to designing a magnet to pull the needle out.
It's a total paradigm shift for you listening. This could unlock treatments for diseases previously considered completely impossible to cure.
It's an incredible leap forward.
So I want to leave you with this provocative thought. If we have AI agents that can rewrite their own code to discover things hidden from human sight, are we approaching a point where scientific discovery becomes fully autonomous?
We might just be.
Thanks for joining us on this deep dive.